Hey everyone. So in this video, I'd like to talk about quadratic equations. So until now, we've really focused on linear equations, right? For example, we looked at in the beginning of our class equations like 3x plus 7 is equal to 28, and we solved equations like this. And as we got more comfortable with solving equations, we tackled more challenging examples, maybe things like 11x plus 5 is equal to 3x minus 8, or even more involved examples where maybe we needed to really do some simplification, right? So maybe something like 5 times x minus 1 is equal to 3 minus 2 times 4 minus 7x. Right, so these are all examples of linear equations. Where the variables that appeared in our equation, the exponents on those variables didn't exceed 1. Right, so if we look at one of these x variables here, well, this is really like saying x to the power 1, right? We're taking 3 and we're multiplying it with x just once. Right? Exponents describe multiplication, and there that exponent of 1 would just say multiply that x variable just once. And usually, right, like we've seen before, when that exponent is not included, it's really implied that there should be a 1 there. And then we also tackled or dealt with equations, linear equations in 2 variables, right? We saw things like y is equal to 4 over 7x minus 1. And in more generality, y is equal to mx plus b. So we got quite comfortable with these things and graphing them and understanding how to look at their inputs and outputs. And so now I like to turn our attention to equations involving variables where maybe the exponent is a little bit larger. Maybe more specifically, I like to focus on examples where the variable exponent is at most 2. And so these are what we call quadratic equations. So equations with variables that have an exponent of 2 and no more, no higher, these are called quadratic equations. So we really made sense of linear equations quite thoroughly, and so now I'd really like to focus on the sort of next step, the next kind of equation, quadratic equations. And so let me just write down a few examples of quadratic equations. So one example might be x squared minus 5x plus 6 is equal to 0. So this is a quadratic equation because I see this term here with our variable x raised to the power 2, and there's no larger variable exponent in this equation. And then here maybe I'll just keep writing down a few more. So let's say we've got 100 plus 3x squared is equal to 50. Same idea is that there's, in this equation, the largest variable exponent we see is this exponent of 2. And we don't see anything larger, and there's no x term there floating around, but that's okay too. Right? We really just are focused here on the largest exponent of any of the variables. Here, maybe another slightly discrete example is x plus 1 times x minus 3 minus 7 is equal to x. So this is a quadratic equation. I see all my variables. I only see an exponent of 1 in all my variables, but really what's going on in this expression on the left-hand side is that those two binomials there are being multiplied together. And when you perform this multiplication, and we'll do it in a moment, I want to say a few things first, but when you perform this multiplication, you'll get an x squared term in there and no larger exponent on the variable x. So this will produce a quadratic term, a degree 2 term. It'll produce an x variable with an exponent of 2. And so at the end of the day, this left-hand side would, it's a quadratic polynomial. So this is a quadratic equation. And we can also write expressions involving other variables. Let's say a squared minus 5 plus a cubed is equal to 17. And here, this example, I just wanted to include it to show a non-example. We have this term with an exponent, this variable here with an exponent of 3. This is not a quadratic equation. In fact, it's a cubic equation because the largest exponent on any of the variables is 3. So when we deal with quadratic equations, there's kind of a preferred format for the equation so that we can really talk about it and deal with it in the most simplest way. It's called standard form. So a quadratic equation is in standard form. Let me highlight this. It's in standard form when written in the form, it's written in the form a times x squared plus b times x plus c is equal to 0. So what this means is that our equation is in standard form if we've moved all of our, all of our input variables, all of our x variables onto one side, as well as the constant term. Right? So this is what we mean by standard form. It's just really all the terms are kind of lumped together on one side of the equation, and we don't really have anything else on the other. And so, if I look at, this example here, this first example we had, this is an equation, a quadratic equation in standard form because we've got the x squared term on the left, we've got the 5x, the x term on the left, and the constant term on the left. And it's organized in descending order of their powers, right? This is like saying this is a standard form equation, a quadratic equation in standard form, where really the coefficient of x squared, that's what we typically call our a term, or a coefficient, that's saying that a is equal to 1. We're looking at a quadratic equation in standard form where a is equal to 1, b is equal to -5, the coefficient of the x term, when everything's moved to one side, and then c, the constant term, this is equal to 6. Right, so what about this next equation on the right? Is this in standard form? Well, it's not. How could we put it in standard form? Well, we can put it in standard form if we move all of the terms, the square term, the constant term, and the linear term, the degree 1 term, onto one side of the equation. And so we can do that by subtracting 50 from both sides. Right? If I take this equation and I subtract away 50 from both sides, well, then we get 3x squared, and then minus 100 and minus 50 together is minus 150. And then 50 minus 50 on the right-hand side would give us 0. So this would be a quadratic equation in standard form because really all of the terms, the x terms and the constant terms, are moved to one side of the equation. And so in this case, here a would be 3, the leading coefficient, or the coefficient of our x squared term. What would b be equal to? Well, b would be equal to 0, right? This equation is really equivalent to 3x squared plus 0 times x minus 150 is equal to 0. And so the b term, the coefficient of our x term, it's as if it were 0 here. And then c would be negative 150. Okay, here, let me make sure that I'm still recording. I would hate to. Okay, cool, great. Everything's going fine then. All right, now let's keep doing this. Let's do this for the last example here, example 3. And let's confirm that it's a quadratic equation. Let's put it in standard form. So I'll rewrite it down here below. So we've got x plus 1 times x minus 3 minus 7 is equal to x. So here, we're asked to multiply, if we wanted to simplify this out, so we could put all the terms on one side of the equation. Here, if we were to multiply this out, right, we would multiply the first terms together to get an x squared This x term would have to multiply with this minus 3, so we get a minus 3x. 1 times x, this next term would have to get multiplied with 1, so that'd be 1x is just x, and then lastly 1 times negative 3. Well, that's minus 3. And then we still have the minus 7 that's outside, and we still have that is equal to x. So let's simplify this left-hand side. We've got x squared is equal to, no, not x squared is equal to x squared minus x and plus x is minus 2x. And then minus 3 and minus 7, that's minus 10, is equal to x. And so to put this equation in standard form, I want all of my x terms, my constant terms on one side of the equation, so I'm going to subtract away x from both sides. And we end up with x squared minus 3x minus 10 is equal to 0. So this is an equivalent form of this equation here, to this equation here. But this is the way to express that equation in standard form, where here we would say that the coefficient a of our x squared term, this is 1, b is negative 3, and c is negative 10. So when it came to linear equations in two variables, where we had a y variable involved an output variable, we spent a lot of time graphing these kinds of equations, and we learned a handful of different ways to graph these kinds of equations. Right, so maybe let me list them down. The first way we learned how to graph a linear equation in two variables was to find some solutions, list them out as a table, and then plot those points. Right? And then we would plot those points and draw the curve that goes through all of those points. So here, one way we could graph a linear equation was by making a table of the solutions to the equation, right? So this really meant plug in values for x and determine the corresponding y values. And as we got more comfortable with solving different kinds of equations, we learned a few different techniques. We learned that if we could find the x and y intercepts, these would be friendly points to determine from our equation. We could plot these 2 points, and we'll align it, it's a straight line. If we know 2 of the points on the line, we really know the entire line. We can really sketch out that full line. And so here, these are the x and y intercepts were just 2 nice points to use to sketch the graph of the line. And so the last technique we learned was using the slope and the y-intercept to graph a line, right? We could, if we had an equation in slope-intercept form, y is equal to mx plus b form, we could see the y-intercept, 0, b. We could plot that point down, and we can see the slope of m and use that to determine other points on our line. So these are ways we could graph an equation. So for example, if I had y is equal to negative 1/2 x plus 1, well, here that would tell me I would have a y-intercept of 0, 1, and my slope of negative 1/2 would tell me I would need to go down 1 and over 2 points to find another point on my line, and I could rinse and repeat that. Right, so here, and then here I just can't emphasize enough that this negative 1/2, that's the same as negative 1/2, and it's the same as 1 over negative 2. So you can kind of use those 2 different interpretations to find other points on our line. But one thing I like to emphasize is that here we see that negative slope, and negative slope tells us that the graph is going down from left to right. And so when it comes to graphing quadratic equations, well, we can't really use the same technique. All of the same techniques, that is. Right? So if I look at these 2 examples here, well, the slope and the y-intercept, this is actually very specific to lines. It's a great method for graphing linear equations, but it's really only going to work for linear equations for lines. These ideas were specific to linear equations. Now, x and y intercepts, these aren't necessarily specific to linear equations, but it's not as clear how we could find x-intercepts of a higher degree polynomial equation. So here, this is something that we'll have to look at in a little more detail to actually use. And so really, if we wanted to graph an equation of higher degree, a quadratic equation, in two variables. And so the kinds of equations I'm referring to are really of the form y is equal to a times x squared plus bx plus c. These kinds of equations. Here we really do have to resort to this initial approach of making a table of solutions, picking some values for x, plugging them into the equation, and finding the necessary values for y. Those will give us some points, and we can plot those points and sketch the curve that passes through all of those points. So here, let's go ahead and do that for one example. So let's graph sort of the most basic example of a quadratic equation, the equation y is equal to x squared. So here this is where we don't have an x term or a constant term, we just have that x squared term that makes it a quadratic equation. And it's got the nicest coefficient a here, the coefficient of 1. So here, let's go ahead, let's make a table. An x and y table, and I'm just going to pick a few different values for x. Let's say 0, 1, 2, let's do 3 as well. -1, -2, and -3. So when we plug in 0 into this equation, well, we get y is equal to 0 squared. And that means 0 times 0. So we really get y is equal to 0 when x is 0. What about when we plug in 1 into this equation? Well, we get y is equal to 1 squared, and 1 squared is just 1, right? 1 times 1 is 1. Let's see let's keep going with this. We've got y is equal to 2 squared. So this tells us that y is equal to, well, 2 times 2 is 4, so y is equal to 4 when x is equal to 2. Y is equal to 3 squared. If we plug in 3, well, that tells us that y is equal to 9, right? 3 times 3 is 9. And now let's do the same thing for the negative numbers. We've got y is equal to -1. Here, this is squared, right? We're squaring whatever number x is, so we're multiplying to itself this number -1. And well, -1 times -1 is +1. And if we plug in -2, well, we get y is equal to, oh, this should be squared, y is equal to 4, right? -2 times -2 is +4. And then lastly, if we plug in -3, well, this gives us 9. And so the squaring forgets about the fact that we've got a negative input here. We get the same results as we see when we plugged in these positive values for x. And so if we graph this, and here let me paste this picture here, this grid to work with. Well, we just want to plot our points now. Plot these points and sketch the curve that runs through these points. Well, here this point 0, 0, let's start there. That's the origin. And we see the point 1, 1, and 2, 4, and 3, 9 is off this grid, but maybe I can kind of imagine that it would be up here. Might not be so precise, but we can just imagine for now. And then here, -1, 1 is another point, right? -1 for x and 1 for y. -2, 4, -3, 9, maybe that's all the way up there again. We kind of get this symmetric picture where, on the left side of the y-axis and the right side of the y-axis, we get the same points. But anyways, let me just sketch the curve that passes through all these points, and maybe I don't need to I don't need to really show it going all the way up there. I'll just sketch it down here on our grid. Again, we want to sketch a smooth curve that passes through all of the points we plotted. Of course, there are many points that fall in between the points we found. That correspond to solutions to our equation in two variables, but those are the points we found from the nicest numbers we could really plug in. And so that's the graph of this quadratic equation, y is equal to x squared. And so typically, when we have a quadratic equation, this is a nice example we have, or that's out there for a quadratic equation, but we can deal with more complicated looking quadratic equations, and really the shape of the graph ends up being the same. We don't get this straight line anymore, we get something that we call a parabola, this sort of bowl-shaped graph. And it has the same feature that it's kind of symmetric about, there's sort of a middle line where the left side is mirrored, as a mirror picture of the right side. But here we get this shape we call it a parabola. And more complicated quadratic equations in two variables give us similar looking parabolas, these bowl-shaped graphs. They might be positioned in different places, they might be a little flatter, a little narrower, they might open up or they might open down. But generally they give us this kind of shape. And so this is a little bit outside of the scope of the class to look into this more deeply or thoroughly. You'll in your future class, you'll encounter quadratic equations and really focus on solving more involved equations and graphing more involved equations. But this approach does always work. This approach of making a table of solutions and plotting those points down. So I just wanted to make it very clear that that's something we can do here to graph these equations that are a little bit different than the ones we're used to. So yeah, they're a little bit more involved than the approaches for graphing these kinds of equations are a little bit more involved than linear equations, graphing linear equations, but not too much so. But I just want to emphasize that our approaches for graphing linear equations don't exactly work for graphing quadratic equations, except for this one here. So now I want to turn our attention to solving quadratic equations, and I want to limit ourselves to some very special kinds of examples. Let's really work with the friendliest examples. We won't cover solving all kinds of quadratic equations. That is a topic for another class. There's a handful of different techniques that you'll have to learn before moving on to later mathematics classes. But let me just talk about one that kind of resembles our approaches for solving linear equations. And so here let's solve the equation x squared is equal to 25. And let's just kind of reason through this. Let's not necessarily talk about a technique quite yet. Let's just reason through this. So anytime we're tasked with solving an equation, what we're really asked to do is to find solutions, but more precisely find all solutions to the equation. And so when we look at this equation, x squared is equal to 25, well, we're familiar with what squaring does to a number. It means multiply to itself. And here we're asked to find what number multiplied to itself is equal to 25. And if you're comfortable with your multiplication table, you might think, well, x is equal to 5 is the solution to this equation, and you'd be right? How can we verify that? If we replace 5 in for the x variable in our equation, well, 5 times 5 is 25. This equation is true. We've found a solution. But now we have to pause and remind ourselves that solving an equation means finding all the solutions to that equation, and we found one. Are there any others? Well, if you think for a little bit longer, you might recall that negative 5 would make sense to plug in and make this equation true, right? If I plug in negative 5, well, squaring a negative number is going to forget about that negative sign. A negative number multiplied with a negative number is going to give a positive result. And so this is going to give us positive 25 as well. This is another value for our x variable that makes the equation true. And then actually there are no others. These are really it. And so some people might rewrite this as x is equal to plus or minus 5, or these are the solutions to this equation, x squared is equal to 25. Right, so these are some solutions that you might have expected, but I just want to emphasize that there are two here, one positive value, one negative value. And if we look at some slightly similar but still different equations, we can apply the same idea, right? If we have x squared is equal to 9 and we wanted to solve this equation, well, the same idea applies, and we might see that the solutions are, or we would see that the solutions are x is equal to plus or minus 3, right? Because 3 squared gives me 9. And if I take negative 3 and I square that, well, negative 3 times negative 3 is also 9. And that would be a solution to our equation. And so here, let me take a moment to point out that this number 3 here, this is the square root of 9. Right, so when we look at this equation, x squared is equal to 9, really what we're saying is that the solutions to this equation are x is equal to plus or minus the square root of 9. And if we look back to our equation above, x squared is equal to 25, and we see the solutions x is equal to plus or minus 5, we can view this plus or minus 5 as plus or minus the square root of 25. Right, the square root of 25 is 5. It's sort of kind of like the undo button to our squaring operation. Right, and so it kind of makes sense that x is equal to plus or minus the square root of 25 would be the solution to our equation. And so really, in general, if we have an equation of the form x squared is equal to some number, right, so the solutions to that equation, so if we have some sort of equation like x squared is equal to just a number here, right, like x squared is equal to 25, x squared is equal to 9, x squared is equal to 16. Really, the solutions to these kinds of equations are x is equal to plus or minus the square root of that number. And so, that's what we saw earlier, but let's go work through a few more examples just to really confirm this. And I really hope this does make sense because, we spent a lot of time solving equations in the past where we tried to isolate that x variable by undoing the operations that were happening around x. And here, if we're squaring x, it kind of makes sense that if we take the square root of both sides in some sense, we get the solutions. We're undoing the squaring action. But here, we have to be a little bit careful. We include this plus or minus because square rooting kind of forgets about the minus signs. So we have to kind of remember to include it in there. But really, square rooting is kind of like reversing the squaring operation. And so let's go ahead and solve the equations now. X squared is equal to 144, and y squared is equal to 16 over 81. I would encourage you to pause the video and try these examples out yourself first. Okay, so this equation x squared is equal to 144. The solutions to this equation are really the same as plus or minus the square root of 144. Right, these are the numbers that square to 144, so they should be the solutions to x squared is equal to 144, and really this is x is equal to plus or minus 12. Right, 12 squared gives me 144. If I plugged in positive 12, well, 12 times 12 is 144, and if I plugged in negative 12, I would get negative 12 times negative 12, that's also positive 144. So these are the two solutions. And then here we can do the same thing. We can say y is equal to plus or minus the square root of 16 over 81. And here this feels a little bit less comfortable. We're dealing with fractions now, and the square roots of fractions might be a little confusing. But here, if we just remember that fractions, when we multiply them, we just multiply numerator to numerator, denominator to denominator. Well, what fraction squared would give us 16 over 81? And notice that 16 is a square, 81 is a square. Right, the square root of 16 is 4, and the square root of 81 is 9. So it feels like a reasonable guess to say maybe 4 over 9. Well, how could we confirm that? We can just try squaring that and seeing if we get the right result, right? If we take 4 over 9 and we square this, well, that means 4 over 9 times 4 over 9. And to multiply these two fractions, we get 4 times 4 is 16, and 9 times 9 is 81. So 4 over 9 is the square root of 16 over 81. Now this is y is equal to plus or minus the square root. Oh no, we just figured out what that square root is. It's 4 over 9. So with all this information, what types of quadratic equations can we solve now? Well, we can solve any quadratic equation, that can be put in the form x squared is equal to k. We saw that really if an equation falls into this form, where we just end up with that squared variable is equal to a number, then we can solve it using this square root idea. And so if we have an equation and we can somehow manipulate it into this form, then we can solve that equation. For example, if I have x squared minus 9 is equal to 55, and I wanted to solve this equation, well, this looks a little bit different than what we've had in the past, but if we add 9 to both sides, all of a sudden it looks like the kinds of equations we were solving just a moment ago. Right, we have x squared, and we just have a number on the other side, and we can rewrite this as x is equal to plus or minus the square root of 64. And well, the square root of 64 is the number that squares to 64, that's 8. This kind of makes sense, right? If I plug in 8 into this equation here, we do see a solution, right? If I take 8 and I square it, well, then we get 64 minus 9, and that does equal 55, like we expect. And we can check this for negative 8 too, but the same idea, the same thing occurs, right? We get 64 minus 9 at the end of the day. And so really this is just to show that here, when we have other kinds of equations, if we get that x squared term alone and we just have a number on the other side of the equation, then we can solve that equation using this idea, this technique. And so let's do the same thing. Let's solve the equation 98 is equal to 2m squared. And really I would encourage you to pause this video and try this example out. This one's a little bit maybe less clear than the one above, but it's not too much more challenging. So here we see this m squared term, and you might feel inclined to try and apply the square root idea, but it's not so clear how we would do that. So really, I really want to recommend that we should get that m squared term alone first. Right? In other words, we should undo this multiplication by 2 that we see here. And if we do that, we divide both sides by 2, right? M squared is being multiplied by 2. If I divide both sides by 2, I would undo that multiplication. I just get m squared on the right is equal to 49. And I know that here, that means m is equal to plus or minus the square root of 49, right? If m squared is equal to 49, m itself is equal to plus or minus the square root of 49, which is equal to plus or minus 7, right? 7 times 7 is 49. And we can double check that, right? Here, if I have m is equal to 7, and I square it, I get 49. I multiply that with 2. Well, 49 times 2 is 98, as we saw a moment ago. Now, what if we wanted to solve an equation like this? Let's say we wanted to solve x squared minus 6x minus 16 is equal to 0. Well, we saw here that if we isolate that m squared term, that squared term, we were able to apply our square root idea. If we try the same thing here, if we add 6x to both sides, and we add 16 to both sides, those would cancel out with the minus 6x and the minus 16 on the left. We get 6x, so there should be 16 on the right, plus 16. It wouldn't quite help us to say x is equal to plus or minus the square root of 6x plus 16. Now this would be true, but it doesn't really help us know what the solutions to the equation are, right? I look at these kinds of equations and I want to know the value the variable should be to make the equation true. And here, this doesn't really help me know that. It kind of gives me this weird way of thinking about x that doesn't really help me know the value, the number that x should be to make the equation true. And so, this technique, it doesn't really help for these kinds of equations here. And when I say these kinds of equations, an equation that really still has that linear factor, or linear term, the x term involved. Right, so solving quadratic equations using square roots, we can't really solve them if there's this linear term involved, this x term involved. Right, so when there's just this x term involved that doesn't include the squares or the higher degree term, then we can't use this technique and without additional work. Turns out later you can, but you have to be really careful, and you have to know some extra terminology and some extra techniques. But we'll save that for another time. So here I'm just going to put a big X through this. So we just don't have the tools to solve these kinds of equations quite yet. So let's do one last example. Here, let me turn my notes over. Let's do one last example. Let's solve the equation 55 minus 3x squared is equal to 7. Now, I would encourage you to pause this video. We have all the tools now to solve this equation, and if you feel comfortable or ready for it, it might be beneficial to try this out yourself first. So, the whole idea here is if we can get that squared part alone and just a number on the other side of the equation, then we can really solve this equation. And so, maybe let me just give a brief analogy. If we had something like 55 minus 3x is equal to 7, how would we get this x variable alone? Well, we would subtract away 55 from both sides. And we get negative 3x is equal to, what would this be, negative 48. And then we would divide both sides by negative 3 because there's, negative 3 is multiplied to that x variable. And so we would get, this would be positive 16. And really what we're doing here is almost no different from that, except we're doing this extra step, right? Here we're just trying to get this x squared term alone. And then we want to apply the square root idea. So let's go ahead and do exactly the same steps. Let's subtract away that minus 55 to get that x squared term closer to being alone. And as we saw earlier, if we subtract away 55 from 7, we get negative 48. And then dividing both sides by negative 3. Right, so we can't forget about this negative sign. This is negative 3 sets of x squared. So we need to divide out that negative 3, and we get x squared is equal to 16. And now we're really set up to use the square root idea. This is going to tell us that x is equal to plus or minus the square root of 16. In other words, x is equal to plus or minus 4. So these are the solutions to our original equation.